Our speaker is Trevor Harris. So he's currently an assistant professor at the University of Connecticut at the Department of Statistics there. He received his PhD from UIUC at the Statistics Department in 2021. After that, he joined Texas A&M as an assistant professor, and then last year he moved from there to University of Connecticut. So he works on various statistical questions that arise in climate science. So his work is very much motivated by challenging climate science. And as a result, he has worked on all kinds of different things, including climate model validation, distribution shift, robust downstream quantification, and so forth. And in recent times, he has been especially interested in this neural operator models and conformal prediction, and especially the combination of the two. And that's what the talk will be about. So his title is Locally Adaptive Conformal Inference for Operator Models. So Trevor, please go ahead.
All right, thank you. And yeah, thank you for that very nice introduction. And thank you everyone for having me here today. So today what I want to talk about is some work we've been doing on uncertainty quantification, and specifically uncertainty quantification for operator models. So, there we go. So first of all, in order just to dive right in, let's talk about what an operator is and what an operator model is then. So an operator is a map between spaces of functions, meaning that if I give it one function, it will return another function. Operators are something we use all the time. So for example, a differentiation operator, if I give it a sine wave, it will return a cosine wave. More generally, I can think of an operator as taking a function like f, the blue function here, and returning another function g, like the red function here. An operator model then is a regression algorithm between spaces of functions. So it is a regression algorithm that takes in continuous functions as input and produces continuous functions output. So an operator model then is very much just an extension of our ordinary idea of regression, where we feed in a vector and get a scalar or a vector out. But now we are taking in a function as input and getting another function out.
That's a quick question.
Of course,
is
yeah.
the operator deterministic or is it random?
In this case, we are going to really just be considering deterministic operators. But if you want to make it random and put priors over the parameters, that is
So
going to be
noise, actually.
Oh, that is something we're going to get to, is about how we handle that. So why should we care about operator modeling? Well, as it turns out, there are many problems that can be phrased as a type of operator learning. And so one of the primary applications is on approximating the solutions of PDE. So there are many works in this area, but one of which I wanted to highlight was this paper from 2020, which introduced the Fourier neural operator. And what they were able to show was they could train an operator model on low resolution simulations of a Navier-Stokes solution, and were able to then run their operator model at a very high resolution, and they could produce predictions given the same initial vorticities as the full numerical solution. So the top row here is showing the solution as produced by the full numerical solver, and the bottom row is showing the operator model's prediction. And the advantage here then was they were able to train this model. And once they've trained the model, you can amortize over that cost, and you can run the model as many times as you want, given as many initial conditions as you want. And it will produce these very high resolution simulations at a much lower computational cost. Another area where these are often being applied now is in weather forecasting and climate emulation. So this paper here introduced a multi-channel operator model, which was used to forecast global weather patterns. And so what I mean by that was, given things like temperature fields, humidity fields, precipitation fields, wind velocity fields, and many other types of meteorological variables, the goal of this model was to forecast the state of these systems up to 5 days in advance in 6-hour increments. And so they were able to show that their model was able to, in many cases, meet or exceed the skill of state-of-the-art numerical weather forecasting systems over these time horizons. And one last area that I wanted to talk about was on using operator models to perform downscaling or to perform super resolution, depending on which community you're coming from. And so the problem here that they worked on in this paper in 2023 was to take these regional climate model simulations that were generated at a 4-kilometer grid and try to predict or downscale them to a 1-kilometer grid. And so again, they were able to show that their model was able to meet or exceed the skill of dynamical downscaling systems, but to do it at a much lower computational cost. Okay, So the idea of operator learning or operator modeling has been around for a very long time. This was studied in functional data analysis under the name of function-on-function regression. And there are many different methods that have been developed in this area, but the primary goal of these types of methods was to perform some type of statistical inference. So it was trying to understand the relationship between the input functions and the output functions, trying to understand the relationship between F and G. More recently, and more pertinent to the work that we're going to be talking about today, are neural operator models. And neural operator models can be thought of as somewhat like a functional extension of a deep neural network, in the sense that a neural operator model is going to consist of a sequence of nonlinear kernel integrations that we're going to be able to train. And these are going to be trained to take in a function F and transform it into our output function G here. And so this is going to act very much like layers in a deep neural network, but we're going to have to specify them in a slightly different way because we're working with functional observation. The idea of a neural operator has been around for a very long time. And in fact, this was studied theoretically even all the way back in the 90s. But it was only more recently that these became very computationally efficient and viable for solving many different problems. And so all the examples that I showed you before were all done using different types of neural operator models. Okay, so neural operators are being used for all these different tasks, and they're being used in a lot of areas where we'd like to perform forecasting and where we'd like to make predictions, but they do not carry an intrinsic notion of uncertainty. So the neural operator, unlike the earlier work in functional data analysis, is not couched into a statistical model and does not have a sense of its own uncertainty or the error process. So unfortunately, UQ is critical for many of the applications where we'd like to apply this. So if we'd like to apply this in weather forecasting, or we're using these to emulate climate systems, the uncertainty quantification or the uncertainty is very important, and in many cases almost as important as the prediction itself. So our goal then was to try and develop a general UQ strategy for operator models. Okay. So there's many different frameworks that we could work in, and there are many ways to try and view an operator model with uncertainty. But the approach that we decided to take was based on conformal inference. And conformal inference is not something that is unique to operator models, but this is a very general strategy for trying to imbue predictive algorithms with uncertainty quantification. And the way conformal inference is going to work is we're going to construct these prediction sets. So it's going to be a procedure that's going to sit on top of our model after we've already trained it, and it's going to allow us to produce these prediction sets. What's nice about this is that we are going to be able to guarantee that the prediction sets are statistically valid, even in finite samples. And so this is not going to require any sort of asymptotic arguments to guarantee the validity of these procedures. And it's not going to require us to place any priors on our parameters and try to learn any posteriors. And it's not going to require any real modification to the training procedure at all. So it's going to be something that we're going to be able to sit on top of the model in a post hoc fashion. What it is going to require is we are going to need to introduce a score function. And the score function is going to be what we use to essentially try to quantify how well our model is making its predictions. So the score function is going to be used to try to measure how well the model does, and it is going to be used then to inform us about the typical sort of error rate of these models. The key here is, and the reason we're able to get past having to make asymptotic arguments and use priors and estimate posteriors, is that at least by default, we're going to have to assume that these scores are exchangeable. So an example of a score function for functional data could be the L2 norm between the output function we're trying to predict and the prediction of our trained operator model. Okay. So if we're good with that, then I would like to just give a quick rundown of the basic conformal inference strategy so that we can talk then about how we're going to modify that for our problem. And so the basic algorithm, I sort of outlined it here, is given some model and given a training data set and then given a calibration data set, where the calibration data set needs to be completely disjoint from the training. So it needs to be an actual honest out of sample set. What we're going to do is we are going to have to first train our model on the training data. And then once we do that, we don't really need the training data anymore. We can dispense with it, and everything will be done then on the calibration. Then using whichever score function we decided to predict to quantify the error rate of our model, we are going to compute all of our scores on the out of sample calibration data. Then what we're going to do is we're going to find the point Q, which is the kth largest score, where K is this point here. It is the ceiling of 1 minus alpha times n plus 1. And essentially what this is trying to do is it can be thought of as trying to find a 1 minus alpha quantile of our scores, and then the n plus 1 in the ceiling are acting as a type of finite sample correction. So once we do that, once we've defined our scores and we found our cutoff point Q, then for any new input function, which we call fn plus 1 here, then the prediction set is going to be defined as all of the responses or all the G's such that their score is less than or equal to Q. And so the way I often think about this is that Q is trying to define a typical range of errors. So if I said give it a miscoverage rate of 0.1, then I can think of Q as trying to find the point which the errors are going to exist around 90% of the time. And then the prediction set is going to be all of the functions within that range. Okay. So standard conformal works very well marginally. So you can show that these prediction sets will have coverage. They will cover the target with at least probability 1 minus alpha. And this is going to hold even in finite samples. So this is not an asymptotic argument. This is something that is going to be true even if you have only a finite sample data. So there's no need to condition on, say, infinite future data. You can also show that the overcoverage or the excess width of these conformal sets is also not going to be too large. And so it's not going to achieve this coverage guarantee by simply making infinitely wide sets. We are going to get prediction sets that at least hopefully somewhat contour to the uncertainty. And what's nice about this procedure as well, and why we opted for this, where we're working in operator models that are very much rapidly developing, and there are many different types of operator models being developed, is that it works regardless of which prediction algorithm we're using. So regardless of how we've constructed that model, we are going to be able to apply this procedure and construct these prediction sets. But the problem that we really were trying to set out to work with is that the prediction sets are not going to be adaptive to any heterogeneity in the conditional distribution. So if there is some type of heterogeneity in the conditional distribution, then the prediction set we get is not going to be able to change its shape, its width, or other sort of geometric properties in response to that. And the reason this is because all these properties are fixed at calibration time, because we estimated all of our scores at calibration time. We found our cutoff point at calibration time. And then our prediction set is going to be purely based on that cutoff value. So I just gave an example here where the residual function is given by this black function here. And this is showing a process where I had the residual that we were trying to cover, and its amplitude and shape were changing as a function of time. And the orange band shows the estimate from a conformal inference procedure where we use an L infinity score. And we can see that it essentially forms a tube. And the tube roughly takes on the form of a sine wave, because that's what I use to generate the shape of the data. And it's not shown here, but at least 90% of the time, or around 90% of the time, it did in fact cover the residual. But we can see that at different points where the conditional distribution is changing, or where this residual process is changing, the prediction set is not adapting. So although it is covering in this component here, the predictions that we get is not very much representative of how the errors look in this region. And so we can end up with things like systematic overcoverage in places like this, and we can also end up with systematic undercoverage in places like this, because that guarantee is marginally over all of the data. Yeah.
What function is this particular?
This, I believe, was just an L infinity score, so that we just got a tube, a little band. Yeah, the blue line was that I mentioned. So the blue line is showing the the band as estimated by our approach. And so I'm just including this here. I was going to mention this in a second, is that to show that this is something that is going to be possible. So it is going to be possible to adapt to this type of thing. Yes.
Question.
Yeah.
If you're using primitive score, coming back overly conservative, if I understand correctly. I mean, if the structure of the error distribution doesn't align with your assumption, then anyone is going to be overly conservative confidence. But this is not the case I'm seeing here.
Yeah. So maybe I didn't understand why would it produce necessarily an overly confident set?
Because you're measuring the error with function.
Right.
If you do this one time.
Yes. Yeah.
If you wanted to measure the understanding of a high dimensional function, usually you have to have a perfect understanding. Distribution, otherwise it's size-wise.
Yeah.
Usually,
Yeah.
35%.
Yeah, so yeah, if this was truly being viewed as functional data where we had like an infinite dimensional problem, then yes, this would end up producing probably something a little bit overly wide, but the guarantee is really not with respect to the type of score we use. The guarantee is more about the exchangeability of the scores. So
I'm talking about efficiency.
yes, yes.
Efficiency-wise.
Yeah, efficiency-wise, yeah, infinity is not going to be the best, but it does make for the easiest because I can just do plus minus the band here. But yeah, that's a very good question. Okay, so there are many approaches that have been developed for trying to make conformal inference adaptive and trying to make adaptive conformal inference. They try to adapt their width or other sort of characteristics in response to the heterogeneity. And so this figure here is just trying to show a one-dimensional example where my input functions f are just given by these points along the x-axis, and the responses g are just one-dimensional points on the y-axis. And so the idea of a local conformal inference procedure is that if we're trying to estimate the prediction set for a new point, fn plus 1, then we should primarily place our weight on the data around that point. So essentially, we should try to localize in, or I'm sorry, we should try to conformalize in roughly a local neighborhood around our new input. And so this has been shown to have very strong performance compared to other adaptive methods such as adaptive scoring and conformalized quantile regression in univariate problems. And so our approach then was to try to extend this type of approach to a functional setting for operator problems. Okay. So I want to quickly define the setting here so that we are on a clear ground. Again, we have our operator model mapping between the space F to the space G. We're going to assume that these function spaces are fairly well nice behaved spaces. So like L2 spaces, essentially they act as a vector space. We're going to assume that we have our training data and our calibration data given by these regression pairs here. And again, these have to be totally disjoint from each other. And for a new input function, we're going to want to try and construct a prediction set. So we're going to assume we have observed some new input function. The n plus 1 is just simply to tell you that this is beyond the calibration data set, and we want to construct a prediction set. We have not observed its response yet. The statistical model that we are assuming for the data, or how we're assuming that the response varies as a function of the data, is that GT is going to be given by a deterministic component of FT, plus an error process. And the error process here is not something we're going to specify directly, but we're going to make the assumption that the errors are varying smoothly as a function of F here. So this is essentially trying to get at the localization that I just showed you on the previous slide, where that conditional distribution is changing with the covariates. And one key distinction I want to make here is that the way we're going to be looking at this is we often observe functional data essentially as these wiggly lines over a domain, like a time domain, which we have up here. And I'm sorry, it's a little smaller than I thought it would be. And this is how we would often normally receive functional data and what the observations look like. But what we really want to be thinking about is not these as a wiggly line over time, but as a point in a function space. And so all of our conformalization is going to happen in the function space. And then we're going to need to find a way to then represent it back in the observation. Oops, that was too far. So our goal then is to try and, given a new function, given a new input function, fn plus 1, we want to construct a prediction set such that we, 1, have the guarantee, and 2, so that these sets reflect the local heterogeneity in the error process. So they are adapting to changes in the variability and changes in the shape of the error process. the way we're going to go about this is we're going to define a test-specific score function that is going to score the residuals with an approximation to the distribution of the Rn plus 1 residual. And we're going to note this quantity as Pn plus 1. And so the way we're going to end up trying to localize is a little bit different than previous localization methods, which define a fixed scoring rule and then take a weighted quantile of the scores. We're going to perform localization directly in the scoring rule, and then we can just take a normal quantile of the scores. And so the hope here then is if we can have such a scoring function, then we can, based on a cutoff of this value, we will be then able to induce a prediction set that should hopefully broadly reflect the scale, location, and shape of that unknown residual. Okay, so in order to do this, we're going to need a couple of tools to build up to how this scoring rule is going to be defined. And one of the primary tools we're going to use is a very classic notion from statistics called data depth, or functional data depth in this case. And so the idea of depth is that we have all these functions floating around in our function space, and we want to be able to quantify how outlying these functions are with respect to some distribution. So for example, we would say that this function up here floating around the top has a very low depth value because it is very far away from the rest of the point cloud. It is not deeply embedded within this cloud. On the other hand, functions like these two sitting here, we would say have a very high depth value because they are sitting very deep inside the point cloud. And so there are many different depth notions that have been used to try to quantify this notion of outlyingness with respect to a distribution. And I just list a few of them here, which try to focus on different characteristics of functional data or different spaces of functional data and how we want to quantify centrality. But the point is that there's quite a few options here. What we want, though, is a well-defined depth function so that we can define, one, a medioid or centroid of the distribution. And from that centroid, if we have a nice, well-behaved depth function, then the depths should be decreasing nice and smoothly and monotonically from the center. So this is implicitly, or eventually we're going to apply this to residuals. So this is implicitly making an assumption that our residual distribution is unimodal and that it has roughly convex level depth. Okay, so if we have some proper depth notion, which I'll introduce the one we're going to use on the very next slide. If we have some proper depth notion and they all decrease nice and continuously from the centroid, then we can use them to define central regions of the distribution. So here's an example of what I mean here. If we have some gamma, we'll pick some level gamma, just arbitrary Greek letter between 0 and 1, then we can define the gamma level central region as all the functions which have a depth bigger than or equal to gamma. So for example, if gamma is equal to 1, then that would just be the centroid of the distribution. And as I let gamma go down to 0, we are going to get these expanding sequences of sets here. And so the point of this is, and why we're talking about this very old classical technique, is that this is going to give us a way to try and characterize, under some assumptions, try to characterize the location, scale, and overall shape of the functional distribution in its function space without having to be able to write down like a likelihood or without having to make some assumption about its behavior. So it's going to give us a non-parametric way of trying to interact with this distribution without having to explicitly know what it is. Okay, so the specific depth function that we're going to use is something called a phi depth. And what a phi depth is a depth function based on usually going to be random projections of your data. And so the basic idea, before I tell you what this means here, the basic idea, the intuition behind why a phi depth or what a phi depth is trying to do is that we're going to take all of our functions that are floating around in function space. We're going to project them onto a random direction or whatever chosen direction that we need. And then we're going to measure how outlying it looks along the projection. We do this over a large collection of random projections. And what you can show is that this will actually be able to characterize how the, this will give us a very well-defined depth of the function in its original space. So this is analogous if you ever work with things like sliced Wasserstein distances, where you try to get a measure of distance between distributions in high dimensional spaces. This is using the same type of slicing idea to try to characterize these distributions in high dimensional spaces, like a function distribution. So we're just probing the distribution by looking at random projections. They don't have to be random. We'll talk about that as well. The way we're going to measure outlyingness along any given projection is through something called a univariate Tukey depth. This is just one choice. There are many choices you could make, and there are many ways you could try to characterize outlyingness. But this is a very simple one because all we're doing is taking 2 times the minimum of the estimated CDF at whatever point we're trying to classify the outlyingness and 1 minus it. So essentially, it's just a 2-sided p-value. So if you're very far on the extremes of the distribution, one of these quantities will be very small, and you'll have a very low depth value. If you're at the median, you'll have a depth value of 1. So it behaves like how we would expect or hope it would behave. And so what the phi depth is then trying to do, just to summarize, although I think I've already sort of explained it, it is trying to measure your worst case outlyingness along projection. And the reason we're doing this is because this is defining a well-defined notion of outlyingness in a function space. And we can show that it meets all these nice properties, such as these different invariances. Moreover, it is also going to allow us to define central regions of distribution. Okay, so this is how we're going to define our scoring function then. We're going to introduce a new score called a local phi score, which is simply just going to be the phi depth of the calibration residual with respect to the distribution of the n+1 residual. So that's, again, Pn+1. Why this is going to be nice is this is going to automatically localize the scores with respect to the test distribution. So it's essentially trying to measure how much the calibration residuals conform to the test distribution. And so points that are very far away from the test distribution or don't conform to it are automatically going to receive very, very low weights. So it's performing the localization directly in the scoring rule by making it conditional on an estimate of the test distribution. And this is also going to give us a very convenient approximation for forming prediction sets because we're going to reach back to that idea of central regions. And essentially the central region, or sorry, essentially the prediction set is going to be a central region of the residuals, then just shifted by the prediction. So there's only one problem with this scheme, which is that we don't actually know what this distribution is. We don't actually know what this Pn+1 distribution is. But actually, this is the other benefit of using a projection-based approach, is you don't actually have to know or be able to exactly characterize that distribution. All we need to be able to do is estimate univariate projections of it, which is a much, much easier problem. So trying to estimate or approximate a distribution over functions is incredibly difficult. Trying to approximate a CDF over projections is super easy. So I won't spend too much time on this because we didn't come up with this strategy. We're just using it now that we've reduced back down to the 1-dimensional space. We are going to estimate the CDF along any projection by just taking a weighted combination. Sorry, I should point with this. A weighted combination of, we're just taking point masses at each one of these projections. So essentially, we're trying to estimate a weighted CDF where the weights are defined by a similarity kernel between the input covariate and the new test covariate that we're trying to measure. And so essentially what we're trying to do is we're trying to form weights that are very large when our previously seen covariate Ft is very close to the new covariate Fn+1. And we're trying to make the weights very small when they're far away. So it is through this univariate CDF that we are performing the localization. So this is where localization is happening, is through these weights. Once you are able to estimate these CDFs, which again is very trivial to do, we just pick some type of localizing kernel. We just use exponential similarity here. Once we can do this, then we can find all the weights, and all of these CDFs can be computed very easily. So they're all going to use the exact same weighting scheme. It won't depend on the projection. So it can all be done in parallel. And so it looks like a lot, but actually can be done very efficient. And once, sorry, excuse me. Once you have an approximation of this CDF, then we can estimate our depths. Once we can estimate our depths, we can estimate our scores. And so just feeds right back up the chain. We would start at the top where we just needed an infimum over depths. To get the depths, we needed the CDFs. To get the CDFs, we need the local weights. So we find local weights, we get CDFs, we get depths, we have scores.
So did you say how to choose the lambda?
No, but I will talk about that a little bit. I will talk about that. Yeah, no, it's okay. It's a good question. It's actually the most, yes.
And you're still using the exchangeability assumption, I guess, over the realization of different functions in the CalDAP state. Like, I'm trying to figure out where the exchangeability, you have this time scale, clearly there's not exchangeability in the time scale.
Yeah.
So over the function realization from that function class.
So, well, we'll get ahead of ourselves. Okay, that's okay. So
Okay, so you're gonna go.
I will talk about it a little bit, but you asked, so I'd like to talk about it. Basically, when we localize like this, we are going to intrinsically break exchangeability because we're specifically conditioning on this data. So they're no longer going to be exchangeable. I won't talk about it too much here, but it's in the paper. We use this sort of recently introduced concept of local exchangeability to try to get a bound on the miscoverage gap. So we're not going to be able to guarantee the exact coverage, but you can specify a lower bound on how far the nominal level and the empirical level are. And that bound will depend on essentially how exchangeable the data are, which in our case will depend on how we set the kernel.
Okay, and again, your data is still going to be realization from one particular function that is realized from that function class. But your data ultimately comes down to one function.
There will be,
Like, the data itself isn't going to be a bunch of functions, it's going to be data points, like actual numbers.
no, the data points, it is multiple functions.
You just, okay.
So we'll just flip back real quick. I'll just show you. So the data, oh, sorry. Where did I go? There we go. The data actually looks something like this here. So this comes from our energy, yeah, exactly, spaghetti plot. So we're treating each one of these spaghetti points, these lines, as a single data point. And that's what I meant by we're trying to do this all in.
Oh, I see. So the whole thing times.
Yeah, exactly. That's literally what this one is. They just happen to be somewhat split. How are we doing? Oh, really good. Okay. I think I was here. One last thing I just want to mention is we try a few modifications here in order to improve the coverage and also in order to improve the sort of empirical performance here. They're detailed in the paper, but I just list them out here. One is that we are going to look at, instead of conformalizing with respect to the covariate function, the test function itself, we are going to look at a perturbed version where we add a little bit of noise here. That ended up helping the localization, so we don't have this exact dependence on the test covariate, but it's something near the test covariate. We're also going to normalize by the slide scale. This basically introduces a normalization mechanic in our estimate of the projections, because the functional data is often going to come on different scales, and we don't want those to dominate our measures of outlying. We don't want the scale to impact it. That's purely optional. One thing that was actually very helpful and we make heavy use of is, instead of comparing the functions directly, we are going to compare feature maps or transformations of these functions. And the one we mostly used was taking low rank Fourier projections. So just looking at low rank Fourier coefficients. I mean, that was very helpful because a lot of the data was simulated scaffolding processes. So, of course, a lot of the information was there. But we also looked at things like functional principal components for other settings. And we also looked at another one, which was using the feature maps from another operator model. So this was something they developed not for operator models, but for other types of conformal inference, where you want to compare the semantic content of your covariate. And so this mattered a lot more in imagery, but we figured we might as well try it for a functional. It works okay. Okay, so then our procedure actually reduces down to essentially the same thing that we ordinarily would do for conformal inference. So we're going to fit our model on the training data. We're then going to apply our new scoring rule to locally score the calibration residuals, conditional on our estimate of the test distribution. Then we're going to rank our scores. And in this case, there's one slight caveat, which is that the depth values are ordered opposite of how we normally would a scoring rule. So in this case, lower is worse. So instead of going all the way up to the 1 minus alpha level, starting at the bottom, we'll start at the largest value, because those are the most conforming, and then just go backwards. So they're monotonically equivalent to each other. If you don't like that, then you can just take 1 minus the score and get back to the original. But this is how they were originally defined, so this is how we're gonna. our prediction set then, once we find this point q in plus 1 here, which is now going to depend on this test point, is just going to be, as I promised, the prediction set would just be our prediction plus all the residuals who have a score bigger than the cutoff point. So essentially, all we're trying to do is find a central region of that residual distribution and then just shift it by the prediction. So hopefully if this central region is able to circumscribe the variability or the overall shape of that distribution, then our prediction set should as well, because we're just making a translation. Sorry, do you have a question? Oh, I thought you were raising your hand, sorry. Then because this is a local procedure, then that means, we're not just going to have this single one cutoff value. We're going to have to repeat this for every single time we observe a new function, and not the whole thing. We don't have to refit the model. We only have to run steps 2, 3, and 4. It does seem like a lot, but actually, because a lot of this can be done in parallel, it is still very, very fast to do. So it's not too much of an excess computation burden. Okay, so in the interest of time, I'll skip over this because we kind of already talked about it. But one thing I wanted to say is that basically the coverage gap here can be controlled, or essentially, I'm sorry, I didn't mean to point with that. The coverage gap here is essentially controlled by our lambda term here. And there's an annoying trade-off with lambda. We parameterized it so that if our bandwidth was 0, we would get essentially no localization. And that way you recover exact conformal inference in that case, or you should. And if we let lambda go to infinity, then all the weights are going to concentrate to a point mass at the test point. So you get basically a step function at the test point. That sounds good, but it's actually very bad because our estimate is based on a CDF. So if you concentrate too much, you're not going to be able to estimate the CDF, which means you're going to get a very poor estimate of the minimum, which means you get a lot of ties and the scores are essentially meaningless. So there's not a great way to choose it other than trying to minimize this coverage gap. That's essentially what we did by just taking a little bit of extra calibration data and trying to find some lambda that would have a lower bound there, or just pick some relatively large term. So unfortunately, a free floating parameter, you can choose it on here. We found actually over a fairly wide range of lambdas, it wouldn't impact the marginal coverage too much unless you made it like really, really large. In which case you just had you had estimation failure and you couldn't estimate the CDF. Okay. To circle back to what we were talking about, how to represent uncertainty. We performed our analysis in the space of functions, which means what I'm really trying to do is draw a prediction set, which is essentially a blob in function space. And a blob in function space is not super useful if we actually want to apply this in practice, right? This is something that exists in almost like a hypothetical, not a hypothetical, but like a theoretical space. And it's not something we can just put on a graph. So the question then was, how can we convert our prediction set into something we can actually use? And unfortunately, for the way we've constructed it here, there was not a way to try and directly compute what the boundaries of this set would be. So there wasn't a way to have a well-defined point which says this is the upper and lower bound of this set. So we just resorted to an ensemble approximation. So it's not my favorite thing to do because it requires extra sampling, but it is very easy to do. We just do a bunch of sampling, and if they're inside the prediction set, we will keep them. If they're not inside the prediction set, we will just reject them. And ensembles are used in a lot of these problems where we're already applying operator models. So for instance, like Klein projections, the uncertainty there is usually represented by an ensemble of Klein models. In deep learning, we often use deep ensembles or Monte Carlo dropout. We also do these a lot with hurricane projections as well. So it's not my favorite solution, but it is a solution that people will often use to approximate uncertainty. I will sort of just skip over this component here because this is just describing how we're going to sample the data. And basically, we're going to estimate some local functional principal components, sample along the components, and then as long as those sampled functions, after we back transform them, are inside the prediction set, we'll keep them and add them to the ensemble. So all the localization for the functional principal components is purely so we have a high acceptance rate. So we estimate some distribution at least somewhat close. Okay, once we are able to sample a band, sample an ensemble, then the way people often report uncertainty is to report these as a band. And what we can do is if we sample a large ensemble, the naive thing or the sort of right thing to do would be to take a min and max envelope of this band. And so these black curves here, which contain the ensemble, essentially represent the full spread of variability that we have sampled. There's also another approach that we're going to make heavy use of, where instead of taking an upper and lower point-wise min and max, we're going to take upper and lower quantiles. And the reason we do this is because there are a few other methods for conformalizing on functional data, which don't conformalize in function space, but they try to guarantee some manner of coverage in the observation space. And so essentially what we're going to try to do is tune those quantiles so that we get coverage that looks a little bit like those other methods, so we can put them on an even footing. All right, so in the last part here, I just want to talk a little bit about our numerical studies to try and verify that this model, that our method works. So as our base model, we're going to use a Fourier neural operator. It doesn't matter too much. We looked at some other simulations where we tried other types of operator models, and the results don't really meaningfully change. And we're going to first look at the marginal coverage of our approach under a range of localization settings. So we're going to look at taking different number of projections, so different number of phi. We're going to look at 3 different types of localizers, and we're going to look at 4 different kinds of feature maps. And for this problem, we generated a very simple very simple data generation, where we just simulate this is Gaussian process data, this fairly smooth Gaussian process data, and just had a nice little deterministic code here. I'm sorry, I dropped the gamma that should be wrapping phi here. So there's a little bit of a deterministic transformation of FXT, plus a heteroscedastic error process. And what we get, this is showing the delta coverage. And I'll say, first of all, it overall is pretty good, especially at a low number of projections. But the first thing you're looking at is definitely this component here, which is showing that there can be some instability in the coverage here. And so the reason we looked into this for a little while, and the reason this is happening is basically because we have a very high number of projections, and we take the minimum over them, because we're taking an empirical CDF, we get a lot of ties. And so we can get a lot of ties if we take a hard minimum, which can introduce some instability into our estimate of the quantile. And so it can result in a little bit of over and under coverage. Evidently, choosing the right feature map, like Fourier feature map, which is mostly what we use, largely got rid of this issue. So I don't have an exact explanation for exactly why that happened, but that is something we noticed across all of them. Otherwise, the coverage is fairly close. There's a slight upward bias, and that's because in order to try to get rid of the ties, instead of using a hard minimum, we would often apply a soft min function. And the soft min function induced a little bit of an upward shift, or a little bit of conservativeness to the prediction sets. All right, so then we're going to look at a few different baselines here. And these are methods that have either been applied to conformal or they were specifically developed for operator models. We're going to use the same sort of backbone model as before and just conformalize using all these different approaches. These two here, which I'm calling conf and super, these are non-adaptive conformal inference approaches. This conf one can be made adaptive because it's based on using principal components and you can add more clusters to it, but we just chose a single one. There is the UQNO method, which is somewhat of a complicated approach, but it is very similar to an operator variant of conformalized quantile regression. And in the UQNO approach, they don't guarantee coverage at the function level. They guarantee this notion of coverage risk. So they allow for a little bit of slippage in their target functions and to still be considered covered. And then there were two other methods, PONet and QONet. These are based on this deep operator net, which is a little bit different than our Fourier neural operator. So it does use a bit of a different structure, and we try to keep everything paired with each other by trying to match the capacity of these models as best we could. One of these is essentially based on adaptive scoring, which is another way of trying to estimate the variance and then try to make a more pivotal score and then rescale by the predicted variance. And then this one's going to be based on conformalized quantile regression. These two methods don't control the notion of coverage that either of the first three methods do. What these are trying to guarantee is the expected rate of your band covering the target. So if your band covers the target on average 90%, that's the thing they are trying to control. And so this made it kind of annoying to compare across all these methods because they are controlling different notions of coverage. And when you have different notions of coverage, you are going to get very different interval scores because some are much easier to meet than others. And covering an expectation is going to be much easier than trying to cover in high probability. So what we did to try to compare ours to the two different types here, we sampled ensembles using a couple different localization settings. So we had two ensembles where we tried different localization settings and we tried to tune the bands so they had approximately the same notion of coverage as the UQNO. And then we did the same thing for two other settings using the same localization setting and trying to approximate the notion of coverage of PONet and QONet. These are the metrics we looked at. This is just detailing the three different notions of coverage. We also looked at how wide the prediction bands are. So we want these to be essentially as narrow as possible without violating coverage. And we also looked at the interval score as a proper score and rule for evaluating interval forecast. And in this case, lower is going to be better for the interval score as long as you are still covering the target. Okay, we generated the data under three different heteroscedasticity settings. The first one is the one that essentially everyone always uses by just inflating the global variance of the functional data. But we also looked at inducing spectral heterogeneity, so having a Fourier approximation to the error function, and then rotating the coefficients around that to get a kind of a weirdly evolving process. And then we also looked at a two-dimensional local heterogeneity, which has introduced a sigma bump, basically. All right, so these are the results. And I know this is a lot to look at, but I just want to point out a couple of things here. If we look at our method on the bottom, we are maintaining the coverage, the functional coverage, so coverage at the level we're trying to control at essentially the 0.9 rate. And so in this case, alpha was 0.1. In this case, these two localization settings ended up getting us a little bit higher coverage, which is something that can happen if our localizer is set a little bit high. We can get up with a little over coverage here. Compared to Conf and Super, which also both control the functional coverage, because these are the way we set them up, they are not adaptive approaches. The interval scores of these two methods tend to be higher than the interval scores of our sample bands. So we were able to sample bands that should be adaptive to that heterogeneity, which means they're able to adapt to the different regimes that we sampled in the data. So instead of having to have one big inflated band that contains everything, we have lots of different little bands that contain locally what they're. If we then look at these first two, which were intended to cover at the coverage risk level as the UQNO method, you can see that we covered essentially at that level. I was able to tune the band well enough. And this method was also covering at its prescribed level of 0.9. And in this case, the interval score in the global problem, we had our interval score was 1.6, theirs was 1.69. So they're basically the same. But in this localization setting, ours was much worse. So it kind of depends on your localization setting. And the same thing largely holds for PONet and QONet. And the same thing basically holds across all these simulations, which is why they're all on here. It's basically the same story over and over again. All right, so I'm going to try to round it out here. Yeah, I'm sorry.
I think your target was 0.9.
That's right, yeah.
So like 0.9 and 9 is bad.
0.9, yeah,
I don't know if it's bad, that's over coverage.
it's bad because you shouldn't be that high. So I have the up arrow there,
Yeah.
just a quick look,
It's the way to be like, yeah.
in general, it should be high, but yeah, it probably should say up 0.9 or something like that. Yeah, so something like this, that's not great. But actually here we tuned this, we were supposed to control the coverage risk at 0.9. It was still over covering, but our interval score was much, much lower than the other method. So in this case, we were able to adapt that local heterogeneity much better than the UQNO method. Even though we were greatly over covering, so we could probably do. So that was fine. Okay. Yeah, I'm just going to talk about two more things then. So one thing we want to look at is the fact that the more points that we sample in our ensemble, the larger essentially the width is going to become because we're just going to keep adding points, so we can't make it any smaller. So what we wanted to know is basically how many times do you need to actually sample that prediction set? And the result is, we looked at the spectral setting here, and we varied the number of sampled ensemble members from 50 to 5,000. And what we did was we tuned the width of the band so that the expected coverage, so the probability the band would cover would be 90%. We tuned it so that that wouldn't change, so that would be stable. And in that case, the interval score doesn't really change. So as long as you have at least this notion of coverage, you can pick another notion, but this one's easier to do. As long as you're not changing the coverage level at the observation level, then your interval score wasn't changing much. And so in this case, there wasn't really any benefit from going, in this case, even going from 50 to 5,000, you were basically getting the same band, is essentially. They're not exactly the same, but their behavior in aggregate was largely. But of course, it cost you more time. So these are I think the most interesting, and what I want to talk about the most, we have to leave, is looking at how well the model performs when there is a bias prediction algorithm and when we add some type of covariance shift to it. So the covariance shift will be on the next slide. This is all on bias. So we'll look at two cases where we added a bias to the validation and test data, and we either added a constant bias function, which is basically just like a sine wave, or we added a bias function that was a little more complicated and would depend on that input function, so that we had this sort of evolving input varying bias function. And so in the constant bias case, our approach was able to, regardless of how large we made the bias, this just pops out from the translation and variance of the approach, in that we were able to adapt our prediction set. The other methods, especially the adaptive method, the way they adapted to the bias here was to simply expand the width of their prediction set. And so instead of just trying to shift the level, they tried to maintain it so that they were always centered at the prediction. And that the only way to capture a large bias then was to make it extremely large. And ours in this case, ours does not require it to actually be centered at the prediction. In fact, the prediction could be even outside of the set. So for better or for worse, in this case, for better. If you add a evolving bias, then yes, this is going to incur some type of penalty, but it's not scaling as bad. So the y-axis is the interval score on a log scale here. We then looked at a distribution shift problem where we introduced some notion of covariance shift to the problem. And so basically the data were evolving continuously through the training data into the calibration data, into the test data in this sort of smooth way. And we just increased the magnitude of how much it was changing. And so again, what we found was that ours was fairly robust to when we introduced local covariance shift and also when we introduced this spectral covariance shift. Okay, and so we're out of time, so I'll skip the real data baselines, but I'd be happy to go back to those later. Basically, the real data baselines were very, very challenging to do, and there were a lot of violations of exchangeability, which led to some very, very weird behavior here. And then I'll skip this about our model discovering extra seasonal variability. So that's it for the talk. The motivation here was that operator models are, in my opinion, a very important development for ML. They don't have an intrinsic notion of UQ, so we set out to try to develop a notion of UQ. And specifically, we wanted to work in a setting where the data was evolving through either a series of regimes or evolving over time. And that's what we consider here, and that is what is a little bit different from some of the previous approaches. And the results show that it worked fairly well. That's all I have. Thank you for listening.